Hi, in this new video, we're going to discuss how to use the linear programming to solve the information design problem. Okay. Solve the information design problem with linear programming. Okay. So now let's see how we are going to do this. So recall that the basic game G, it has some elements, had some ingredients. So we have the action set AI, UI, and for all those decision makers, I, and a state space, omega, and the prior mu naught. Okay, so an information designer can choose the T information structure. So T just includes S and pi, right? So the signal realization for each decision maker and the information structure, the signal itself, pi. And they choose, the information designer chooses this. Okay. Chooses the T to maximize their objective function. Okay, so V, so this is sort of the utility function, right, for the information designer. So this is a big V. It's just a map of the product of the state space and the action space to a real number. And where they assume that the best B and E for them, for this, the designer, is played. Okay. When designer is played. Okay. So this becomes equivalent to the following problem. Okay, so we can write this as the maximization over the outcomes. So this outcome is an element of the BCE of the G, right? BCE of the basic game. Okay. All right. So we sum over the A and omega and multiply all those outcomes with the big V, the utility. Okay. All right. And this BCE is just the set of the base correlated equilibrium of the basic game G. Okay. So after that, then we can use the linear programming. So use the linear programming. So specifically, we're maximizing by choosing the outcome. So this is a real number with dimension of the cardinality of omega times A. Okay. So all those kinds of combinations. And our objective function is the summation over A omega and the outcome times the utility. Okay, so what are our constraints here for the linear programming problem? So those constraints are just the requirements that we need to satisfy for the BCE, right? So subject to, first is the consistency, and then the second is the obedience, right? So the consistency is that the summation over A and all the outcomes, we have the marginal probability over the state equals to the prior, and for all the omega within the big omega. So this is the consistency, and for the obedience, okay, let's just take some note here. Consistency. Okay, this is obedience. So you can always refer to the previous video to see the definition for the BCE, for the base correlated equilibrium. Okay, and those two things are just the requirements for that solution concept. So this is summation over AI omega, and we have an equality here. So AI v of AI a minus I omega. So this should be small v. Don't mix up this v with the big V. So this is small v here. This is just the outcome. And times the UI AI a minus I omega. Okay. Which is, so this is the case they are listening to the action recommendation, and so they should have a higher or the equal expected utility rather than the deviation. So the deviation yields this utility here. So the summation over AI omega. So all the same, but we just replace the AI with AI prime, okay, with a deviation for the player I. Okay, just copy and paste. But here we add prime, okay, so that's the only difference. Okay, and this is for all the I's and all the AI and AI prime. Okay, good. And also we need to have the outcome to be a non-negative number, right? Then this is true for all the A's and omegas. Okay, so that's how we are doing this problem, solving this problem in the form of the linear programming, okay? And that's pretty straightforward. Okay, now let's consider our classical example, our old example with the judge and prosecutor, and see how we are going to solve that by the linear programming. So the player is just a judge because the prosecutor is the information designer, and we don't include that into the I's. So a action includes convict. This is just the abbreviation for the convict, and acquit, okay? And the state can be guilty or innocent for a certain person, and mu naught, the prior of G, is 0.3, and prior of I is 0.7. So the utility for this judge, if the state and the action matches, they match, then the judge has utility of 1, otherwise it's 0. So namely it means that utility of convict, bad guy, or acquit, a good person, gives 1 utility. Otherwise, if convict an innocent person or acquit a bad person, gives 0. Okay. So the information designer is the prosecutor. Okay. So the prosecutor's utility, we use the big V's. So the prosecutor just wishes to convict the person, regardless of whether this person is good or bad, okay, is guilty or innocent. So it doesn't matter for the prosecutor. So that's the assumption of this game, the setting, the basic setting for that. So convict, G or I, both give 1. Otherwise, acquit gives 0. Okay. So those are just the background of this game. And so here, remember that doing the linear programming, this means that we're actually choosing the V's, right? So now we're looking at the V's, little V's, the outcomes, not the big V's. The big V is the utility for the sender, for the information designer, but the little v is the outcome. The outcome, recall that, is nothing but the joint distribution over the state and action. So this is the outcome. So the outcome of convict, a bad guy, and we let this be x for us to be easier to solve this linear programming problem. So v of convict I, and we set this to be y. So because we have the marginal distribution of the marginal probability of the v over the state equals to the prior, so here, although we have this, but we can actually write this to be 0.3 minus x, right? Because this plus the first v should be equal to the prior 0.3 for the g person, right? Okay, so similarly, acquit I is 0.7 minus y. Okay. So namely, our x and y should be between those reasonable intervals. Okay. All right. So that's the setup for us to start to solve this linear programming problem. So the task we are doing here is just to choose x and y, right? So that's the thing that we're going to do that. So because we have those utility functions, we have those zeros and ones, so we can further simplify our objective function. Okay. Right. So from all the way up to here, right? Okay. So we can just assign those zeros to the v's, either small v's or big v's, to be either if they're 0, then we can just assign the zeros to them and ignore those terms, and just leave those other positive numbers in the objective function. Then after that, we can just rewrite this problem as the maximization over the x and y's. Then this becomes simply x plus y. Okay, so this is just after the simplification using those utility functions and the v's. Okay, and similarly, the constraints is simplified to. So here actually we haven't write the constraints yet, right? So actually here we will. Okay. So here we will first have the obedience. Okay. All right. So for the obedience, and first let's check the convict. Okay. So for that action, we have x. So x times. So this is just should write just a dot. X times 1 plus y times 0. Okay. This is the case when the judge is listening to the advice, when the action is convict. Okay. And this should be greater than or equal to the deviation case. So this is x times 0 plus y times 1. Okay. So this is the utility from deviation. So that's the first constraint. Okay, for the obedience. And for the second one, if the action is acquit, then similarly we have the utility function from the listening to the dice. This should be 0.3 minus x, right? And this we multiply by 0. Okay, and plus 0.7 minus y times 1, and this should be greater than or equal to the case where there's deviation. So correspondingly, this is 0.3 minus x times 1. And we can always verify those results, right, from the numbers later, if you wish to do so. So, and plus the last term is that this is 0.7 minus y times 0, okay? So this is the deviation, which has a smaller utility. Okay, and we copy and paste those. Okay, and that's the constraints that we are going to use, right? Okay, now let's start to solve this problem. Okay, so this simply becomes maximization with x and y. So where the objective is x plus y, subject to x is greater than or equal to y, right? So we derive from the first inequality. Okay. And then from the second, we have 0.7 minus y greater than 0.3 minus x. So this becomes x greater than or equal to y minus 0.4. And actually this, we do not need this, right? So because the first one implies the second, okay? All right, so, and of course we have those little things here, just copy and paste. Okay, good. So now we can draw our little picture to solve this new programming problem, okay? You can just use a two-dimensional picture, x and y. Okay. All right, so x is between 0 and 0.3. Let's suppose that this level is 0.3. And correspondingly, this is sort of 0.7 for y. Okay. So we have to have something in between of those lines, right? We just label those lines. Okay, and what else? So we also have x greater than or equal to y, right? So it means that let's just draw a 45-degree line. Okay. So this is x, y less than or equal to x, right? So this means to this direction. Okay. So the feasible domain or the area that we're going to maximize over is this, right? So that looks pretty straightforward. So our objective function is x plus y. Okay. So let's just let z to be x plus y. So y is z minus x. So it has a -1 slope, and it's just a straight line. So and obviously we have this maximized if it is crossed with this dot, right? If it goes through this dot. So we simply draw this line here. Okay. All right. So that's where we get the maximization. Okay. So here, and correspondingly this y has a level of 0.3 as well. And recall that we have already solved that problem, this persuasion problem multiple times, and this x is 0.3, y is 0.3. So this those numbers, they maximize the v, okay, and this also corresponds to the concavification result that we derived from the original Bayesian persuasion approach, where we solved that game previously, right? Okay. So then we can actually verify the consistency or the equivalency between those two methods, two approaches, right? So we just recall that. So our in the optimal persuasion, okay. So the pi is a map from the omega to delta s, right? So the s includes g and I, and we just write those pi again for us to compare, okay? So s given, so this should be I, not s, given g, 0. So this is 3/7, and I is 4/7, okay? Recall those results from previous videos. So, and actually, those pi's, they can be just calculated or they can be derived from the outcomes, okay? How do we do that? We just use the V of convict G and divide it by the unconditional probability of the G, right? Either unconditional probability of those outcomes, actually. Convict G plus V of acquit G. So this is nothing but 0.3 over 0.3 plus 0. And this is 1, which has to be the same as the pi GG, right? Okay. So if there's the axiom recommendation, then under the G state, okay, then this little g, it actually has the outcome of the convict, right? Because of the guilty. Okay, so that's the first part. And we can also verify if the state is I, okay? And suppose let's also verify the convict part, the small g. So V of convict I over V convict I plus V of acquit I. And this is nothing but 0.3 over 0.3 plus 0.4 is just 3/7, right? And this should be the same as pi of G given I, okay? So from here, we can see that we have verified that those two approaches, they have the same results. And of course, they have the same result because we have already proved those things, right? Rigorously. So prove the equivalency. So both approaches, they have their own advantages, right? And the information design approach can solve the problem with multiple receivers more naturally, right? Because of the settings. But here, the information design approach, it has more technical ways, such as the linear programming to solve those problems, and it looks more straightforward. Although it doesn't look very easy to understand, but overall, after we have gone through all those steps, then now we can understand that this is more straightforward to us to solve this more complicated problems with the information design context, right? But here, actually, because of the linear programming, so here we have to require that the set of A has to be finite, and it has some, of course, it has some limitations for that. But overall, those two approaches, they're quite the same, right? They're equivalent to each other. Okay, so this is the example, and for the information design problem using the linear programming way to solve that. And later in the future episodes, we can introduce another more general example where the information design problem involves multiple receivers or the multiple decision makers, and let's see how we are going to use the linear programming approach to actually solve those more difficult problems. Okay.